Hello everybody, this is Monisha from SPC Department of Computer Science and Engineering. Today I am going to discuss about 2D transformation and the computer graphics. Now let us move to the today's content. Today we have the content to that introduction, homogeneous coordinates, translation, rotation, scaling, and finally the conclusion. Now, now let us see one by one. Firstly, we have introduction to transformations. What does transformation means? Transformation means the changing of some graphics into something else by applying the rules. We can have various types of transformation such as translation, scaling up and down, rotations. When a transformation takes place on a 2D plane, it is called as a 2D transformation. Now we will see one by one how the 2D transformation will take place using the translation, scaling and rotation. Before that, transformation is plays an important role in computer graphics to reposition the graphics on a screen and changing their size or orientation. We'll know that how the orientation will done and reposition of the models and transformation and resizing it will be done by using transformation in 2D transformations. Before that, now we will know about the homogeneous coordinates. What is meant by homogeneous coordinates? To perform a sequence of transformation such as translation followed by the rotation and scaling, we need to follow a sequential process. But to do the transformation, we have the sequential process by one, such as translation, rotation, and scale. First, we have to do the translate of the coordinates. We have some coordinates, and we have to do that translate the coordinates and then rotate the translated coordinates and then scale the rotated coordinates to complete the composite transformation. To shorten this process, we have to use the 3 by 3 transformation matrix instead of 2 by 2 transformation matrix. If we use 2 by 2 transformation matrix, this process will be more and lengthy. Instead of that, we can do this process by using the 3 by 3 transformation matrix. To convert the 2 by 2 matrix into 3 by 3 matrix, we need to add an extra dummy coordinate, that is W, means windows or anything else, anything means by W. It's a dummy coordinate to transform the 2 by 2 matrix into 3 by 3 matrix. In this way, we can represent the point by 3 numbers instead of 2 numbers. As we know that in a 3 by 3 matrix we need a 3 points and in 2 by 2 matrix we need a 2 points. So in this representation we have 3 points, which is called as homogeneous coordinate system. Homogeneous coordinate systems is nothing but the representation of a transformation translated points in the 3 numbers is instead of 2 numbers is called an homogeneous coordinate systems. In these systems, we can represent all the transformation equations in a matrix multiplications. Any Cartesian points, that is p, x, y, can be converted into homogeneous coordinate by p dash of xh, yh and h. These are the Cartesian coordinates of a homogeneous coordinates p, x and y. Now let us see how the translation will be done in 2D transformation. Translation. A translation is moves an object to a different positions on a screen. Translation is nothing but moving an object from one position to the other position in a window screen, and you can translate a point in a 2D by adding a transformation coordinates. Transformation coordinates is nothing but tx and ty. It's a coordinates which represent the homogeneous coordinates to original coordinates x and y to get the new coordinate x dash and y dash. After translating an object from one position to the another position from the screen on the screen, we will get that a new coordinates x dash and y dash, which is originally coordinates by of x and y. From the figure, we can write that x dash equals to x plus ty and y dash equals to y plus ty. This is, we can see here x dash and y dash, and that is x dash equals to this x dash point, this is x dash point, this is equals to x plus tx. This point, this field, and this field, this actual x-axis, and the transformation position or translation coordinates is and dx, that is x dash is denoted by x plus tx and y dash is denoting by y plus ty. This field tx and ty is called the translation vectors or a shift vectors. The above equation can also be represented using the column vectors. These are the column vectors we can represent the above equation, translation equation, that is p equals to x by y. This p point equals to, this is the actual p point, the original p point and coordinates having a x and y. This is the transformation point, that is p dash. P dash with the coordinates x dash and y dash. And this point can be represented in the column vector form, that is p dash, p is equals to x by y. This x-axis divided by y-axis is having the p point coordinates, and p dash is equals to x dash and y dash. Therefore, the translation vector t is equals to tx by ty. This also can be written as p dash is equals to p plus t. When we had this p coordinates, original coordinates with the translation coordinates, we will get the transform coordinates, final 2D transformation coordinates after adding the original coordination with the translation coordinates. This is translation of 2D transformation. Now we will see the rotation. That will rotate the point with an angle theta from its origin. In the same way, in a 2D transformation, we will rotate the objects from a original position to the some angle to get a transformation. In a rotation, we rotate the object at a particular angle theta from its origin. From the following figure, we can see that point x pxy is located at an angle phi from the horizontal x coordinate with a distance of r from the origin. This is the distance r. This is the point p of coordinates x and y. This is having a distance of theta phi. This coordinate p, the point P with the coordinates of x and y is located at an angle R. The point P with the coordinates x and y is located at an angle phi from the horizontal x coordinate with the distance of r from the origin. This is the origin, this is the distance r, and this is the angle phi. Let us suppose you want to rotate it at an angle theta. After rotating it to a new location, you will get a new points of p dash, y dash and x dash. When we rotate an object from one position to the another position, we'll get a new points p dash, x dash and y dash. This is how the new points will be. As same as the translation, your rotation also will get a new points. Using a standard trigonometric original coordinates of p, x, y can be represented as, we will use the trigonometric original coordinates, so that x is equals to r cos theta or cos phi is an x coordinate. We can call it as equation 1, and y coordinate will be y is equals to r sin phi. Sorry, this is the first time I'm writing this. Sin phi, we can call it as an equation 2. Now we will see in the same way we can represent the point p dash and x dash and y dash as x dash is equals to r cos of the phi plus theta is equals to r cos phi plus. In the same way, we can represent the point p dash, x dash and y dash as x dash is equals to r cos of phi plus theta and y dash is equals to r sin of phi plus theta. This will be resolved in the form of r cos phi into cos theta minus r sin phi into sin theta, and y dash is resolved as r cos phi into sin theta plus r sin phi into cos theta. This is the equation form of cos of a plus b and sin of a plus b. After solving this all equation 1, 2 and 3, 4, we'll get the coordinates x dash is equals to x cos theta minus y sin theta and y dash is equals to x sin theta plus y cos theta. In the form of simplified form of the equation is equals to p dash is equal to p into r. When we multiplied the original p coordinates in from the rotationary coordinates, that is rotationary coordinates is nothing but r cos theta or cos phi or sin phi, will get the rotational 2D transformation points p dash, whereas the rotational matrix is nothing but this one. This is the rotational matrix. This rotational angle can be positive and the negative. We can see that here negative also will be there and positive also is there. 2D transformation by rotation. Now let's see scaling. How scaling can be done in a 2D transformations. First of all, what is scaling? To change the size of an object, scaling transformation is used. Scaling is nothing but the change in the size of an object. Is neither be increasing or decreasing or up or down. This all be done by scaling. In the scaling process, you have either expand or compress the dimensions of an object. Expand means increasing of the size and compress means the decreasing of the size and the dimensions of an object. Scaling can also be achieved by the multiplying the original coordinates of an object with the scaling factor to get the desired results. Also, how we have done the translation and rotation as same as scaling can be also be done by multiplying the original coordinates from the scaling coordinates. In the translation, we use that original coordinates and translation coordinates. In the rotation, we use that original coordinates and rotational coordinates. Now here we can use that original coordination and scaling coordinates. Now let us see what are the scaling coordinates, how are the scaling coordinates will be used in the scaling transformation. First, we will assume that original coordinates are x and y. The scaling factors are sx and sy. These two are the original coordinates and the scaling coordinates. And the produced coordinates are x dash and y dash. This can be mathematically represented. Scaling can be achieved by the multiplying the original coordinates by the scaling factor. First of all, what are the original coordinates? Let us assume that original coordinates are x and y, as scaling factors are sx and xy. This are can sx and sy, and the produced coordinates are x dash and y dash. Produced coordinates are the final transformated coordinates. These are the produced coordinates. from the original coordinates and the scaling factor. This can be mathematically represented as shown in the below. This transformation of a scaling using scaling can be mathematically represented as x dash is equals to x into sx and y dash is equals to y into sy. As same as translation and rotation, this also be same format. And here also the scaling factor s and xy scales the object in x and y directions respectively. This Sx and Sy scales the object x direction and the y direction. As you know the directions, this is y direction and this is x direction. This scaling factor will scale the object in the x direction also and the y direction also. And we can represent it in the form of p dash is equals to p into s. As I told in the beginning, this can be produced coordinates are done by the original coordinates and scaling coordinates multiplication. The same we are representing in the form of letters and the symbols. Whereas scaling is SSS scaling matrix, as I told, SSS scaling matrix which contains the scaling factors. The scaling process as shown in the following figure. Let us see the figure. Before that, I should explain this. Before that, if we produce the value less than 1, the scaling factor is, then we can reduce the size of an object. If we give the value of s as less than 1, we can reduce the size of an object. If we produce the value greater than 1, then we can increase the size of an object. Now let us see that with an example. See, this is one graph and this is one graph. When we give s value less than 1, the object size will be decreased, reduced. And when we give the s value greater than 1, the object size will be increased. As we show in this diagram, we have given the size of an s is less than 1, so the object size will be reduced. And in in the another diagram, we have given the size of an s value of an s is greater than 1, and the size of an object is increased. Like this, we can form the scaling of an 2D transformation. This is how the scaling of an 2D transformation will be done. Now let us move to the final part of this today's content, that is conclusion. And in the conclusion, we have learned about the four. We are at the end of the today's video. Uh, we are the Now let us come to the conclusion. In the conclusion, we have learned about the four main types of 2D geometric transformations. One is homogeneous coordinations, translation, rotation, and scaling. And each type has its own unique characters and it can be represented to transform the objects in different ways. As we know that translation is a one form of unique character which repositions the object in the same window. And the rotation is nothing but it rotates the objects in the same window. Scaling is nothing but the increasing and decreasing of the size of the object. Each type has its own unique character and it can be used to transform the objects in a different ways in a 2D geometric transformations. It is important to understand this transformation because they have a particular application in the field such as computer graphics, robotics, and architecture. As we know that computer graphics have a wide range of applications and robotics and architectures. Architecture uses the computer graphics. For the computer graphics we uses in computer graphics they use 2D 3D transformations to see the virtuality of an constructing building or something bridges or anything else, monuments or anything else. They will create, and first they will create the graphical models using this transformations. From that they can recognize the designs and modifications, what else to be done, what else not to be done. As also they will analyze using this 2D transformations. And robotics, for the generation of and designing the robotics, they will use that they will use the 2D transformations to analyze the designs and how the design will work on the robots. And computer graphics, we all know that we have huge applications using the 2D transformation and 3D transformations. 3D transformations also done as same as translation, rotation and scalings. For example, computer graphics software uses the transformation to create realistic 3D animations. As I said, architecture, robotics, computer graphics all uses the 3D animations to analyze the architects and buildings design, complexity, shapes and robotic designs, its models, all to be done by the using of the transformation. So this is very important to understand these topics. While architects use them to design the buildings with the complex shapes. I've already told why the architecture has an important application by the transformations. They can use this for design of buildings with the complex shapes. As the technology continues to advance, the need for experts in a 2D geometric transformation will only increases. Nowadays the technology is growing rapidly and drastically in advance as we going, we need to the experts in a 2D geometric transformations will only increases. There is no decreasing in the demand of 2D transformation experts. So it's very important to learn the transformations in a form of 2Ds and 3Ds. I encourage you to continue learning about this topic and explore how it can be applied in your field to interest. However, whichever the field you are learning and whichever the field you are doing that, please continue this exploring the transformations using this 2D transformations and 3D geometric transformations. It will the increase the scope, never decreasing the scope. This is a rapid increasing in the scope and it will never decreases its scope. So I suggest and I'll encourage to continue learning of a 2D transformation and 3D transformations. It will help you on a career and future. If you have any doubt, please let me through to the comments. Thank you for watching, and if you have any questions, please comment it on. Thank you.